Now we have our last section within the algebra unit of our SAT, looking at graphs of systems of inequalities. And we looked at these a little bit in a previous lesson as far as word problems go, and we're just going to look at some more fundamental ways of how linear inequalities are graphed specifically. So when we learned about linear inequalities, we saw that multiple values can satisfy an inequality. So how do we graph an infinite number of xy values to satisfy an inequality? We do it by shading the xy plane. A linear inequality is defined by a line in the xy plane which divides the plane into halves, half of which have our solution set. Which half we shade depends on the inequality sign of the equation. So, three-step process. We want to write an inequality in slope-intercept form. Y is whatever inequality, mx plus b. If the inequality is greater than or less than, then we will graph a dashed or dotted line to show that any points on the line are not included because we don't have the or equal to part. If the inequality is a greater than or equal to or a less than or equal to, we will graph a solid line to show that those points are included. If y is greater than mx plus b, we want to shade above the line, and if y is less than mx plus b, we shade below the line. So here over to the right, we have an example of y is greater than x. We graph the line y equals x, and then we dotted because of the greater than symbol, and because it's greater than, we shaded above the line. So let's go ahead and look at a couple more examples. I'm going to graph the following inequalities and then identify if the given points are a solution to those inequalities or not. So we have our first equation in slope-intercept form, so we can graph it just like we would y equals negative 1/3 x minus 2. We start with our y-intercept at negative 2, and then we have a slope of negative 1/3, so we go down 1 and right 1, 2, 3 to get our next point. Once we have our points, we can connect them into a line. But because we have a greater than sign and not a greater than or equal to, we actually don't want a solid line like we traditionally do. We want to include a dotted or a dashed line. So I'm going to get my straight edge out here, and I'm going to go ahead and redraw that line. And we want to make sure that it is dashed to indicate that any point that is on that line is not a solution to that inequality. Then we look to see where we shade. Since it's greater than, about that, battery on my pen died. Since it's greater than, we are going to be shading above the line. And so our shaded region, I'm going to use a highlighter, is this whole area up here, above the line. Anywhere above the line is where our shading will take place. So let's go ahead and look at these points and see if they are solutions or not. So the point 1, 1, we go right 1, up 1, there's the point 1, 1. It's in our shaded region, so that means yes, it is a solution. The point negative 3, negative 4, down 1, 2, 3, 4, and left 1, 2, 3. The point negative 3, 4, it is outside of our shaded region, so no, it is not a solution. And then we have our last point, 0, negative 2. Well, that's our y-intercept right here. Now, it's on the line, but because it is a dotted line, it is not a solution. No, it is not a solution because the line is dotted or dashed. Next, we can go ahead and graph the next inequality. Now we have the inequality in standard form, so x and y intercepts will actually be a little bit easier, but if you wanted to write it in slope-intercept form, you could. So let's look at slope-intercept form would be y is less than or equal to 3/2 x minus 2. Be careful with the direction of your inequality sign. Notice how the coefficient here is negative. So we'll need to flip the inequality symbol around when we divide by negative 2. And once we have it in our slope-intercept form, we can look and see Let's go ahead and graph this line with a y-intercept at -3 and a slope of 3, 2. And we could continue plotting that if we wanted to, keep going with our line. And because it is a less than or equal to, when we draw the line, we can actually just draw a solid line straight through all the points. We do not dash it because of the or equal to. And we look and we see, well, the inequality is less than, so we're going to shade below the line. So we're going to go to the underside of our line, and we're going to shade this area in. And let's go ahead and look at a couple more examples for points. We have the point 1, -1.5. So 1, -1.5 is located right about here. 1, -1.5. Now, that is on the line, just like in the last example, but our line is solid. That means all those points are included. So yes, this is a solution. Then we have the point 4, 1, 1, 2, 3, 4, 1 within our shaded region. Yes, it is a solution. -2, -4. That is a point outside of our shaded, so no, it is not a solution. Last thing we'll look at is graphing our systems of inequalities. So whenever we have two intersecting lines, our plane is always divided into 4 regions. Points in each of the 4 regions represent solutions to a different system of linear inequalities. In the graph here, we have the equations defining the 4 regions as y equals 3x minus 2 and -1/3 x plus 4/3 x. So here we have y equals 3x minus 2, and up here we have y equals -1/3 x plus 4/3. So using this as a guide, what we can do is look for the 4 different systems that we could have. There's some slight variation, so we could have more, but this generally covers all 4 regions. Identify 3 ordered pairs that are solutions to the given system. Okay, so what we're going to do is kind of look at each line and see where the shading is going to take place, and we can identify some points. So let's start with, let me change this to black. When we look at our first one, we have shading above the line on our 3x minus 2. So any shading in this region here above the line. And then for the other inequality, anything below the other line. So anything that's in this overlapping region. And so since we're looking for where these areas overlap, the green region shown here is actually where our system has its solutions. And so any point in this green region, such as the point -1, 1, or the point -3, -2, these are all points that satisfy the inequality. Also, anything that is on this line, let me do that in a different color, on this line, still can't see that. Try one more time. Anything on this line here in this section will also be a solution due to the or equal part of the inequality. So again, anything within the green region will be a solution for that first system. For the next one, what we're doing is we're looking at, let's see if I can get a slightly darker color for that. So anything below that line, that color's awful. Anything below the line with 3x minus 2, so anything below the line in this region. And then anything above the line on our other equation, which is this region up here. So we see that the overlap is this purple area in this section here. So any point that is found within that purple region is going to be a solution, such as the point 2, 2. Point 2, 2, or the point 4, 1. These are solutions to that system. Let's find another one since we're looking for 3. 3, 2. Those are all solutions in that purple region. Next one, we're looking at y is greater than 3x minus 2. So again, we're above the line on this side. And then y is greater than our other equation, so we're above the line. And the overlap is the pink area. Anything in this pink area here. So we can get a few points, such as 0, 2, or even the point 1, 2, or let's say the point -4, 3. All of those are solutions in the pink area. And last but not least, by process of elimination, we're probably looking at the orange area, but let's make sure. Anything less than our line 3x minus 2, which is on this side, and then anything less than our other line, which is on this side, that intersection being the orange area for sure. So we can go ahead and erase that. And we can identify any point in that area, such as the point 2, -1, or 3, -3, or 0, -4. Okay, and again, there are an infinite number of points in those shaded regions. Those are just some examples for where we can find some solutions.